Hello. Today we're going to go through chapters 3 and 4 um, to get ready for our semester review. So starting with chapter 3, maybe I should write chapter 3 somewhere. Chapter 3 is about examining relationships between two variables or bivariate data. Now I could also say 3-4 because 4 is about that too. Chapter 4 just moves to when it's nonlinear bivariate data. All right, so starting up, we need to know that the response variable measures the outcome of the study, and the explanatory variable helps us explain uh, or influences change in the response variable. Usually, the explanatory is the x, and the response, I don't know what kind of a r that is, but the response is on your y-axis. Now, a scatter plot is what we use to describe them. So we have your x variable here, your y variable here, explanatory response, and then you plot the values associated with that. Now remember that you should label both of your axes when making any scatter plot. When we interpret a scatter plot, we look for the overall pattern and then striking deviations from that pattern. Now the thing is that we really need to put in here, we need to say which direction. Is it positive or negative? What form? Is it linear or nonlinear? And the strength of that relationship. Is it a strong relationship? Is the R value high? Is it a weak relationship? Is the R value low? And if there's any type of outlier, then you have to put that. Some outliers are just outliers, and others are influential points. An influential point is an outlier that will change the least squares line and the R value. Now, keep in mind, each part of this description should be in context. So you should say if I'm describing this over here, I would say um, there is a fairly strong positive linear correlation between the number of beers and your blood alcohol content level. So you need that context in order to have a good description. And like we talked about, when describing direction, you want to either say if it's positive, going up, negative, trending down. Now, our correlation R uh, can be figured out with this formula. It's like the z-score for the x value times the z-score times the y value, um, and add up those for every single data point, and then divide it by n naught minus 1, and you get your R value. Um, most of the time, we can find our R value in our calculator by typing the data points in list 1 and list 2 and just doing linear regression, and that'll give you your R value. Now there's properties of R. These are pretty important because they tend to pop up on multiple choice answers or questions. There is no distinction between explanatory or response variable. So if we switch the x and the y's, the R will stay the same. So if we flip-flop these, R stays the same. R does not change if we change the units. So if we change it from centimeters to inches, the R value is still the same. A positive R means there's a positive correlation, and a negative R means there's a negative correlation. Um, so positive R means it's going up, negative R means it's going down. R is always between negative 1 and 1. If R is closer to 0, it's a weak correlation. If it's closer to 1 or negative 1, then it's a stronger correlation. Also, correlation requires both variables to be quantitative. You cannot use categorical variables with correlation. Correlation does not describe curve relationships, only linear. That's why in chapter 4, when we have curve relationships, we try to linearize them. Correlation is not resistant to outliers, so one big outlier can really throw off your R value. And correlation is not a complete summary. You still have to talk about means and standard deviations and other stuff to get a full picture of the data. Here's just a general idea on what an R value of 0 looks like. That's pretty scattered. Negative 0.3, there's kind of a negative direction. 0.5, it's starting to get stronger, but it's still kind of a moderate to weak positive linear correlation. Now, at negative 0.7, you can see that it's getting closer and closer. And zero point 0.9, much stronger, 0.999. This is negative, but it's still a really strong correlation. So just so you have an idea on what those numbers represent in a graph. A regression line is a line that can describe how the response variable changes with the explanatory variable. Uh, I think you have that down pretty well. The predicted value is our y hat value, and the true value is our y value. So whenever we have a residual, we take our y value that we have, and we subtract our predicted value to get our residual. And a residual is just the error. So when we have a bunch of scatter plots, and I draw a line like this, the residual is the difference vertically between that point and the line. So you take your y value and subtract out what we would have predicted it to be with the line. Now the equation of a least squares regression line, we say y hat equals a plus bx. The mean of x and the mean of y are always on that line. So we could replace the x with x bar, y with y bar. And remember, these x bar and y bar is the mean. We also can figure out the slope by taking our correlation coefficient, multiplying by standard deviation of y over standard deviation of x. This is a formula that you can use on the AP exam. This is given to you. Extrapolation is when you are predicting things outside of your data set. So if your data set goes from 20 to 50, say, if they tell you to predict what happens when your x value is 70, that would be extrapolation. The data, the linear correlation might be good here, but we have no idea what happens outside to the right or outside to the left. Residual plots are when we plot our residual values on our y-axis, and we plot our x values on our x-axis, or explanatory variables. And our residual will look something like this. The more scattered, if we have a really scattered residual plot, that tells us that our linear regression is a pretty good fit. If there are any curves or any patterns, then we think that there's the original data probably isn't linear. Our r squared, it's also called the coefficient of determination, is the fraction of the variation in the values of y that can be explained by the least squares regression of y and x. It's something common that they ask on the AP exam, and it's good to know that exact wording. It's just taking the r value and squaring it, for the most part. Now, we need to know how to read a minitab result. What can we find out from this? Well, we know that the dependent variable, our y value variable, is going to be our height. This right here is our x variable. This value is our slope. And across from constant, this is our y-intercept. We'll learn about most of this other stuff next semester. Oh, and r squared, r squared. R squared would be 0.871. So if we want to find our r, we just have to square root 0.871, and that would give us our r value. Now, if we wanted to interpret these, to interpret the slope, I would say for each increase in one arm span, the height increases 0.84. If I want to interpret the y-intercept, I would say when the arm span is 0, the height is 11.54. If I wanted to interpret r, since the slope is positive, our r will be positive. And if I take the square root of 0.871, I get 0.932 or 933. So that's a strong positive linear correlation between arm span and height. If I want to interpret r squared, then I would say 87.1% of the variation in height, the y variable, can be explained by arm span. All right, let's keep it moving. Oh, and then we're done with chapter 3.